Okay, so moving on. So the last thing we're going to cover in the course is correlation and regression. Now, mostly regression. We'll talk a bit about correlation today, I'm sure. Was that covered in 2126? Did you do correlation coefficients are?
Yes.
Yeah, thought so. Did you talk about regression at all?
No.
I can't remember.
Okay. Yeah, I mean, it's not. It gets a little advanced on the regression, which is what we're gonna do. So this is a bit of a different way to look at things. Perfectly acceptable, nothing wrong with it. It's just that it's a little bit different than what we've been doing with analysis of variance. So everything we've dealt with so far has been about differences between means. Right? That's really all we talked about. We talked about going back to t-test, then analysis of variance, is all about mean differences. In a longer, well, the other way to look at this is it's not just about a difference between means. It's also the relationship between the levels of an independent variable and the levels and the values of a dependent variable. Okay. So if you've got like A1 and A2, two levels of A, and then you've got two different means, we can say that the dependent variable, that's the means, varies along with the levels of A. Okay? So it's not, I mean, it's a somewhat different way of looking at it, but it's the same kind of question. Now, with a variable that is a sort of, we have A1 and A2 that had a dichotomous variable. Maybe you've got a categorical variable of some sort, low, medium, high, or even something numerical, 5 minutes, 1 hour, 24 hour for an interval for some memory experiment. It seems like an odd thing to think of. On the other hand, with a continuous variable, or a variable that isn't necessarily continuous but that has many, many discrete levels, it's kind of easy to see these kind of relationships and think about them that way. So here's an example, and I completely made this up, and this is using a scatter plot. This would be your income in, I don't know, let's say thousands of dollars a year. And this is your IQ. It's not that tight. I am close. There's a pretty good positive correlation, but it's not that tight. We could go low, medium, high, and we'd find an effect. We'd find a difference. I mean, that would be something we would easily find. On the other hand, we'd lose a lot of sort of fidelity if we did that, because we have these individual values. So why not use all the individual values instead of grouping it into, say, low, medium, and high? Why don't we just use all the values of IQ and all the values of income? Okay. So that kind of thing. There's a lot of things in social and life sciences that actually are like this, where you get very many different levels of something. Well, in science in general, and then you can measure. And as I said, those are just numbers I made up, so it's not like it's that tight. The correlation between IQ and income is about 0.5. That's more like what a 0.8 something. If only it were so. So the scatter plot's actually a really useful EDA tool. So if you're going to do exploratory data analysis, which is something we talked about really early in the course, and you've got different levels, you're very often going to use a scatter plot. You're going to print that out just because it's going to be a useful thing for you. Okay. We use a way to standardize the variable relationships, even if they have different scales. It shouldn't affect us if the income is in dollars or euros. Or you know, whatever the value is, or cents versus dollars. So you need a way to standardize that variable relationship, even if they're different scales. Height and weight correlate. If you plotted height and weight, it's really quite striking, as you can imagine. But it should, if we're going to standardize what that relationship is, it should be the same if it's height in inches or height in centimeters, or weight in pounds or kilos or stone if you're in the UK, right? 14 pounds in a stone. No, I'm serious, that's a thing. Whatever, right? So a start for this section called covariance. I mentioned covariance the other day when I talked about analysis of covariance, and I talked about looking at variance that overlaps, and this is a way you can quantify it. So what covariance, the covariance of x and y is just you take x, y pairs. Okay? So these are pairs. So again, so that would be the income, the IQ of somebody and their income. That's an x, y pair. Somebody's height and somebody's weight is an x, y pair. And you have to calculate the mean for x and the mean for y. And then what you do is you sum up this product of x minus x bar times y minus y bar divided by n minus 1. You can see it looks a lot like a variance. In fact, if this was x minus x and x minus x, right, it would just be x minus x bar and x minus x bar would be the sum of the x minus x bar squared, just like we're using for a variance. So this is the variance that two variables share. You're going to have to, in the next week and a half, 2 weeks, when we finish up this course, start thinking about variance as a thing you can touch, an actual thing you can imagine. It's a hard thing to do, by the way. So don't expect me to get it right away. But if we have the variance in x and the variance in y, this is how much the scores vary. The covariance is where this overlap happens. Okay? That's all that is. Covariance is the overlap in variance between two variables. The variance they share. So you have to think of variance as a thing, and that they share a part of this thing. And I know, as I said, I understand that's not easy. Questions so far? Does that make sense? Now, what this does, as I said, is it measures the degree to which two variables vary together. You can see, by the way, that unlike regular variance, this has a sign. Because if as one goes up, the other one goes down, as altitude increases, temperature decreases. Those things you learn in grade 5 geography and memorize. So if one of them is above the mean and the other one's below the mean, you're going to get a negative value for covariance. It's totally fine. And the sign simply indicates the direction of the relationship. It doesn't talk about, you can have negative covariance, it's not a big deal. Okay. The sign basically talks about what ways the graph goes. If it's going up, it's a positive variance, a covariance, I'm sorry. If it goes down, it's a negative covariance. Okay? So if we were to draw an imaginary line between it, if it's a positive slope, you get a positive covariance. If it's a negative slope, you're going to get a negative covariance. You see that? Makes sense. Okay? The thing is, we want a measure of association. We'll have to standardize covariance, so the scale doesn't matter. Because that number's going to get bigger if the scale's bigger. So if the income was in cents, that number's suddenly going to be bigger. We want to be able to, as I said, standardize it. So covariance depends on the standard deviation of x and the standard deviation of y. Doesn't it? I mean, think about it. This is a measure of variance among things. It depends on how much variance there is. That's what it depends on. And if you want to standardize something, you divide by what it depends on, basically. So that's what we're going to do here. We're going to divide by the product of s sub x and s sub y. And that's going to give us what's called R, the Pearson R. Or as it's also known, the Pearson product moment correlation coefficient, which no one calls it, everyone calls it R, which is R. You shouldn't just call it R because there's a lot of different kinds of correlation coefficients, but Pearson R is fine. So that's the covariance divided by the standard deviation of x over times the standard deviation of y. So this is going to standardize it so it doesn't matter if your heights are in inches or centimeters. If your income is in euros or dollars. Okay. So if the absolute value of the covariance of x and y equals the standard deviation of x and y, standard deviation of x times standard deviation of y, then the absolute value of r equals 1. And you have a perfect relationship. So absolute value, that's those two bars on the side of the R mean and the side of the covariance mean. All that means is just the absolute value of the score irrespective of sign. So the absolute value of -7 is 7. The absolute value of 7 is 7. So you have a perfect relationship, perfect predictive relationship actually. You have complete overlap in the variances if you have a correlation of 1.0. They're in fact measuring the same thing. If I was to measure your height in inches and your height in centimeters and made a scatter plot, I would have a straight line. And I think just intuitively you know that the variance of your heights in centimeters is the same, if you're thinking variance is a thing, as the variance of your heights in inches. Right? Because it's really just two ways of measuring the same thing. What this is actually getting at is how much are we measuring the same thing? That's really what a correlation coefficient does. How much are we measuring the same variance? So if we have height in inches and height in centimeters, we have a perfectly straight line. And it's positive correlation. If we have dopamine 2 binding efficacy and effective dose of an antipsychotic drug, we get a straight line. It's basically 1. Anybody who tells you that schizophrenia is not caused by a problem with dopamine 2 receptors doesn't know how to read. That's what it is. You look at it. Just ask them to explain that perfect straight line. And then when they wrinkle their brow in a vain attempt to understand a graph, just walk away. Just walk away. Just walk away. So if we actually get a perfect relationship like that, what that actually tells us is we're measuring the same thing. It's like your height in inches and your height in centimeters. Okay? And that's obviously an absurdist example, but it is measuring the same thing. So the sign then is simply going to tell us about the direction of the scatter plot. All that does is show you the direction. So R can only go between -1 and +1. The closer it is to 0, the smaller the relationship. It cannot be less than -1, and it cannot be greater than +1. It is impossible. And if you look at mathematically sophisticated among you, should actually get that by just looking at this. There's no way this can be bigger than this. If these are exactly the same, it's 1. It can't be any bigger. If it's bigger, you did it wrong. Or the computer did it wrong. Nobody does this by hand. Like a question I often ask when I teach this stuff at the intro stats, which I've taught since like 2009, but when I teach the 21-26 class, is on quizzes, I'll often say, Kenny calculated some correlation coefficients, because it's an alliteration. And he got the following: -0.7, +0.4, and 1.7. Which one is the biggest correlation? And first of all, it's whatever I said, -0.7, and +1.4 or whatever, that's not a correlation coefficient. Kenny made a mistake. Right? That's impossible. So this just tells you the sign. It's simply telling you about is it what's called a positive relationship? As one goes up, the other one goes up. As one goes down, the other one goes down, one variable. Or is it a negative relationship? As one goes down, the other one goes up. Questions so far? This is stuff I think you know. I don't think it was probably introduced to you like this. But it's computationally the same thing. And in fact, this is the way it was derived, and then there's a computational formula that's given with, I forget what it even is. I just don't care. This makes more sense to me, and I would never do it by hand anyway, so no one does it by hand. Even with 10 numbers, all you have to do is select the two things in, well, I use Google Spreadsheets and type in equals Corel, and then this data set, that data set. It's, oh, look, correlation. It's done. Right, so you can do that with Excel, you do Google Spreadsheets. Of course, you can do it with SPSS. Something to remember. This only works for straight lines, straight line relationships. So, if we had taking a look, if we had an example like this, let's say we're doing a dose-response curve with a drug. Very often, the dose-response curves, your response is on the y-axis, sorry, and your dose is on the x-axis. Very often, you get something that looks like that. Goes up, goes down. It's not usually quite that pretty. And in fact, if you got that, you'd say, oh, look, a perfect relationship. And you get a covariance of 0. You get a correlation coefficient of 0. You'd literally get 0. Is there a way to calculate a correlation with this kind of distribution? Mm-hmm. Sure. It's a curvilinear relationship like that. It's easy to do. This assumes straight lines. All you have to do is assume you have, in this case, say a parabola. And then you can do it. What you're doing is fitting a different kind of curve. I'll show you in a second the basis of how to find these curves. And you're sort of fitting this curve, right? All these methods are for fitting straight lines. Okay. So if you had this beautiful relationship like that, you get a correlation of 0. If you have a relationship that looks more random, so you just have a whole bunch of dots, you can't make a prediction. Let's make that a bit better. Well, no, there was a correlation there for a second. I can't predict X from Y. Yeah, Jay.
What are the equal signs doing?
Doing where?
Right there in the.
This?
Yeah.
R, -1 is less than or equal to R is less than or equal to 1. They're doing what equal signs do. So, other question. So you see this? Like, it could be that if you come out with a correlation of 0, this is the case. And in fact, it's more likely with most of the variables that we end up looking at that it's this. But it could in fact be that you have this beautiful, perfect relationship. This is why you do exploratory data analysis. You look at the stuff, you look at the scatter plot and go, oh, well, that's not an appropriate way to analyze this data. And it's not like there's aren't ways to do this. It's totally doable. In fact, with SPSS will do it for you. You just have to tell it what kind of relationship you have instead of a straight line. All right, questions so far? Is it good? You okay? You've learned about correlations before. It would be so neat if we could somehow predict y from x. If you could give me the x value and I could give you the y value. Okay? And in fact, you know that this happens because you've been to the doctor now and then, and they will weigh you, or they'll take your height and they'll weigh you, and they'll say, you're exactly the weight you should be, or you're a little bit, or you should weigh too much. Or you might get the wonderful thing, you're too thin, start drinking milkshakes. Right? That's the one I was hoping for, right? Really, more milkshakes, more butter. Just eat big handfuls of butter every day. You'll be fine. Doesn't happen. Doesn't happen. But what they've done, actually, they've got data from thousands and thousands and thousands of people, is they can predict weight from height, and they know where you should be. This is something, in fact, that happens a lot, and most of you guys, probably none of you have kids, and if you do, fine, sorry, I missed you, sorry. But you know that when you bring your kid in, your first kid, you bring your kid in to the doctor, and they weigh them and they measure them. And kids don't have a height and they have a length because they aren't standing up. And they say, oh look, he's this long, so he should be this weight, right? And then they'll tell you, oh well, you should know your kid's in this sort of whatever percentile. It's really pretty interesting. Typically, it's like, oh, your kid's huge. That's what we got with John. Your kid's just, look at the size of this kid. He's a giant little man. What they're doing is they're making a prediction. They're predicting weight from height.
Oh my god.
Or in that case, like.
And
it's a pretty common thing. So in fact, we know it's possible. So really, there's a lot of ways you could do this. Let's say we have a scatter. Let's make a scatter. And I'll put a real relationship in this time, not like a real linear relationship. This is my favorite part of the whole course, because I get to do this. It sort of feeds. I mean, I think I might have a touch of autism as well. It kind of feeds it. Okay. Very nice. Okay, so we got a nice positive relationship there. I can tell you probably that's a correlation of about 0.7 something. It's a nice high correlation. Fine. Let's draw a line through these points so we can make a prediction. Well, we can eyeball it. That looks good. That's one way to go. So is that better than... that looks good too. Okay, it's not bad. And also the sort of between those. Oh, we could force it to go through the intercept. And that's not ridiculous, by the way. That's the technique that's sometimes used. There we go. Those are all pretty good, actually. How do we pick? We could do now. The other day I talked about exhausting degrees of freedom. We want to be able to draw a line and not have points fixed. We want to make a prediction. We don't want to do a description. So I can exhaust the degrees of freedom. Right? I can connect all the points. But is that a useful prediction? No. I have to have the points first. It's a completely useless prediction. So that's not what we want. We want to be able to make a nice straight line. But as I showed you, that I think it'd be hard to choose between a few different straight lines. So what we end up using is what's called a least squares regression line. So I fixed this morning. It looks like this. Here's some points. Okay. There's a 4-point scatter plot. I didn't feel like making any more. So these are the y's. This prediction line is called y hat. A little circumflex, we call it a hat. I've always wondered if in French you say y circumflex or you say y chapeau. You don't know. I got one friend who does enough statistics that he'd know the answer to that, but I keep hoping he's going to be at this conference. I haven't talked to him in a long time, so it'd be a weird thing to just email him out of the blue and say, hey, Sylvain. Because he'd be like, why haven't you emailed me in 5 years? So I hope he's at the conference I'm going to in a few weeks. Does a lot of dog cognition stuff. Cool guy. He's from University of Moncton, he's Quebec City. And he'd know, because he teaches stats. So I'm going to have to, I always forget to ask him. But it's y hat. I know it sounds silly. It's a y with a circumflex on it, but we call it a hat. Cute. So we've got y, those are the actual points, and y hat is a prediction. And what we've got is these differences between the predictions and the line, between the y's and the y hats. So what we're going to do is we're going to make that as small as possible. These are errors. These are mistakes. The line's wrong. That's the right answer. The point here. The line that we drew, the prediction, y hat, it's wrong. But let's make it as not wrong as possible. So we've got these deviations from the line. we want to make that as small as possible. And you probably know, or well, at least guess, because in a way the line's almost like a running average. What are we going to get? These deviations are going to sum to 0. Well, so they're always going to cancel out. That's no good. Just like variance, what we're going to do is we're going to square them. So we're going to sum the squared deviations of the real values from the predicted and square them. And then we're going to minimize that quantity. We're going to minimize that quantity. Now, you guys, you may not remember doing this, but in probably about grade 9 or grade 8, you started, maybe grade 9, you started doing, you did minima and maxima of functions, and you'd find the minimum and you'd find the maximum. So you know that if you could do it when you were 14, this is actually mathematically a pretty trivial issue. It's not like this is a hard thing to do. We don't have to draw an infinite number of lines and try to find out which one has the smallest sum of squared deviations from the line. This is something we can do. I'm not saying you can do it right now because you've probably all forgotten how to do it. But it is something you did, unless they've totally changed how high school works since I went. We learned that in grade 9, I think it was grade 9 math with Mr. Stevenson. Also my football coach. The man that told me after I pulled the ligaments in my right knee to get up and walk it off. Football. My leg got bent. About like that. So I'm like, it was in practice. This is the thing. It's in practice. And we're running these drills. And he'd lateral you with the ball. And then he'd yell the blocking bags. And the blocking bags are very big. And they had different numbers. So like in football plays, they tell you those numbers actually mean something. They're not just random things the guys say in the huddle. And they'll also do this. Okay, you go here. Like, this actually plays, right? So we would be yell 2, and you have to go between this got a certain hole. So they yell 2 or 4 or 3. Laterally the ball. You're supposed to run and you put your head down, and you're supposed to get tackled. So it's like it's practicing carrying the ball, practicing getting hit, and then the guy practices hitting you. It's all very fine. Now the first time through, he yells out 4, so I go between the left tackle and the left guard because that's the number 4 hole, and I run, and I actually do a little move, a little juke move, and I fake the guy out, right? So he can't hit me, and coach pulls me over by my face mask because that's how coaches used to pull you over because that's what he did. He's a really good math teacher, by the way. And he says, Broadback, you're not O.J. Simpson, which now is a compliment. But then it was, you're not a running back. You're a defensive tackle. Just run straight forward with your head down. Okay, so next time they called it like a 3, so I go between the right tackle right here. And I cradle the ball like that. I put my head down, and I'm running, and I'm expecting to get hit somewhere up here because you're not supposed to go at somebody's knees even in a game because you could kill somebody. But this dummy clips me right below the right knee. And I'm down on the ground, my leg is bent a little bit. And I'm screaming at the top of my lungs, fuck! It hurt! And the coach comes over and goes, Broadback, you okay? That's what he says. That's his reaction. I said, my effing leg isn't supposed to effing bend like that, sir. And so I threw the sir, which I thought was good. And I get up, and it's sort of straightened out. It wasn't bent. It wasn't that horrible, but it was noticeably bent. And I got up, and he says, walk it off. So I arm around the other guy who could hit me was kicked off the team right away. And I walked, my knee hurts right now. So I'm walking like this, and my arm around, I walked home from school, which is about 2 miles. And, well, no, it's 15 years old. And then I went to the doctor the next day, and I said, can I play? Because I'm an idiot. This is on Tuesday, play on Thursday. She said, if it doesn't hurt, you can play. But I think it probably hurts. I said, well, if I tape it up. So my knee hurts. Right now. 30 odd years later, my knee hurts. The sad thing is, why does any guy play football? To impress girls, because that's why guys do everything for their whole lives. Didn't work. So, anyway, interesting story. Mr. Stevenson taught us how to take minima and maxima of functions. See, it all comes back. Life is a rich tapestry, guys. So, we want to minimize this thing. We had 2 guys that ended up playing pro ball on our team. One of them wasn't me. Oh, no, one guy. Yeah, one guy. If you would have picked blue bars. You see these are mistakes, right? You got to understand this. These are mistakes. This line is wrong. These points are right, but we want to minimize those prediction errors. Do I have to put the explicit tag on the YouTube video now? Because I said, anyway. So you end up with what's called a prediction equation, and it's y hat equals a plus bx.
Did you put that line there? Is that what, like, you did the line, or the line?
Oh, the line actually gets calculated.
Oh, wow.
Yeah, it's not like you, because like I said, if you did it this way, you'd have to pick all the possible lines. There's an infinite number of lines. Some of them are horrible, going the wrong way. But there's an infinite number of lines. If we did that, it would be, you could never get this done because you would constantly calculate. So what actually happens is, it's easy to minimize a function. What you're doing is you're getting a minimum of the sum of each y minus y hats. It's actually a pretty trivial mathematical thing. I'll show you in a second. But what you end up getting when you solve this is you get y hat equals a plus bx. That's the predicted y equals the intercept plus the slope times the x value. And now you're all going to tell me, no, b is slope. But I'm going to tell you, no, it isn't anymore. It was when you were in y equals mx plus b in high school, right? Sorry. Not in statistics. And by the way, you know what gets even worse? Next class, this a becomes a b.
What?
Yeah. The more general version of this, so this is the sort of, when you want to just talk about regression, this is called simple linear regression. You do y hat equals a plus bx. When you talk about a more general case, it's this. So it's y hat equals b sub 0 plus b sub 1 times x sub 1. Okay? That's the more general case. So just warning you now that eventually, like when we start talking about multiple regression, it looks like this. Not like this. But they're the same thing. We just change the names. Change the labels. Okay? So you get it. And this is nice because you can describe a line, a straight line like this, with an intercept and a slope. Right? And again, thinking back to grade 9, you remember learning that, thinking, I'm never going to use that. Ha! Right? When you learn about functions. So, predicted y equals the intercept plus the slope times the x value. And Cassidy was interested in how do we calculate this. I think you maybe all were. It's easy to calculate b. It's the covariance of x and y divided by the variance of x. So it's not like you have to test every line. That's nice. And a equals the y bar minus b times x bar. Y bar is the average y score. X bar obviously is the average x score. So what this gets you now is a line. If you got to calculate, first of all, you already have to calculate standard deviation of x. I mean, again, if you were doing this by hand, you never would. But if you were, standard deviation of x is an easy thing to calculate. Now you have variance. You already calculated the covariance. Piece K. And once you have B, you get A. That's easy. Solving for an unknown. All you're doing is solving for a single unknown. This is not a complicated procedure. And again, it's not like this is something people do by hand anyway. But I want you to know how it's done by hand just so you can have some understanding. And what this does, what these two calculations do, is they actually minimize the sum of the squared deviations from y. It gives you a line that has the least squares, the sum of the least squares. It minimizes the sum of squares regression. Well, you think, yeah, you thought else variance was gone, didn't you? It's going to creep back in. So it's minimizing the sum of squared deviations, which is in fact, when you think about it, sum of squared deviations is what analysis variance is all about. Questions so far? Because we've gone pretty quickly. Well, there's not a whole hell of a lot of stuff I can say about this. What I'm saying is, We're here now. Do you have any questions? Before we get on to some stuff that kind of concludes it, in all honesty. And I want you to have a feel for this. So you see what's happening. We get a bunch of data, and we want to be able to make a prediction. We want to predict y from x. It's an interesting research question when you think about it. Because typically we think about what? We think about relationships between our group means different. Here we're trying to say, can we make a prediction? And we often do this, right? You think about, there's a lot of different kinds of linear type relationships we have. And we want to know what we want to be able to predict. Well, let's just think of a symbol before we think of something sort of psychological. You actually can calculate my salary because there's a formula for making up our salaries. There is what's called a floor, the lowest possible thing you can have at that rank. It's this. Plus the number of years you've been working times what are called PTRs here, progression through the ranks. There's salary raises every year. So if you went and you got our union contract, which is in fact a public document, and you knew how long I worked here, and you knew what my rank is, associate professor, you could figure out how much money I make. Or you can wait till May 1st when it's published in the newspaper. On the who should we steal from list.
Yeah, really.
And I'm supposed to be ashamed of it too for some reason. It seems to me guys are trying to publicly shame me for making money. I feel really bad about those 9.5 years I went to university. But see, that's the case, in fact, and it's interesting because if anybody does have a salary that's different than that, there's a mistake that's been made. So one of the things that we do whenever we negotiate a new contract, now it's coming up this year actually. One of the things that you do when you get your first new paycheck is you check to make sure it's right. Because, and I'm not saying they ever do anything wrong. They wouldn't do anything wrong on purpose. But sometimes a buddy of mine once got, this wasn't here, some Newfoundland, got overpaid for a year. And he had to pay it back. Because it wasn't his money. And he kept telling him to. No, it's right. No, it's not right. I think he saved the money was the smart thing to do. Right? So I can actually look and see it's this plus this times this. So that's how much money I make. Okay? In fact, a lot of sort of union contracts, things like that, are set up that way. There's a floor, and then there's steps. So it's pretty reasonable to be able to figure something like that out. So you can predict what, in fact, you can predict it perfectly. There is no prediction error. There used to be prediction errors. It was weird. Some people were overthinking it. It all got fixed years ago. So let's think of some psychological variable. What do you want to predict? I'm just going to show you how this works. We're not going to actually collect any data. What's some psychological variable that we're interested in? How about the ultimate dependent variable? Lifespan. Oh, yeah. Okay. So how long you live, that's what we're going to predict. What's something that varies either negatively or positively with your lifespan? How about number of cigarettes you smoke? Number of years you smoke cigarettes. Let's just go with that, make it easier. We know that correlates negatively with lifespan. Right? It just does. It's not healthy. It makes you look cool and grown up, but that's a joke. So we can say that how long you live equals some number, I don't know, let's pick a number, 80, minus, and this is going to be way off. No, maybe not. Let's go with 0.25 times the number of years you've smoked. That's probably too high. Or that's too low. Yeah, let's make it 90. Okay. I'm not saying that's correct. I'm trying to make it vaguely, just even vaguely correct. It isn't. But let's pretend. And we know there are way more variables than number of years you smoke that affect your lifespan. We know that. So what we do is we measure a whole bunch of people how long they live, and we measure how many years they smoke cigarettes. And we come up, we do these calculations, and we end up with this. So then we can plug in, we can then make a prediction. If you smoke for 4 years, we are predicting you're going to live to be 89. You see that? Because it's 90 minus 0.25 times 4, which is 1. Listen.
So we're saying that a person who doesn't smoke at all would live to be 90?
Yes.
Okay.
Now, of course, we're going to be wrong on some of those. Some people don't smoke at all and die at 50. And some people don't smoke at all and live to be 102. And some people smoke and live to be 100. Okay? So we know it's going to be, it's not going to always be right, but we can make a prediction. Right? We'll be able to make a prediction. So that's, in essence, that's what the MD's doing when you go in there and they figure out your height and say, you should weigh this. They basically plugged in, well, they didn't know that, but they've got a chart. But what it is a regression equation. That's all it is. That's all it is. Okay? And again, we only have one variable in there. We know that there's more than one variable affecting lifespan, because if there was only one variable affecting lifespan, we would be able to very confidently say that everyone dies at 90 if they don't smoke, if assuming this model is correct. And we call this a regression model. It's not correct, of course, but for illustrative purposes. Does this make sense? You see, this is how it works. And you can see this would be kind of useful if you'd say something like, I don't know, how about aggression and a lot of socioeconomic variables. Like how, so you want to predict a score on we have an aggression scale. You can have aggression, and let's predict your years of education. Or go the other way, let's predict aggression from education. Maybe it turns out more educated, you have less aggressive people. Doesn't explain me. I'm actually a really nice guy, but I play an asshole at work. But yeah, see, so you can make these kind of predictions. You can see this very useful. Okay. Questions about that? Does it make some sense now going through like an example? Again, we didn't get the data, we didn't get the covariances. We calculate this. I just made those numbers up. Does it make sense? Okay. So let's interpret one of these. How do we interpret it? A, that's the intercept, or B sub 0, if you want to start calling it that already, would be fine, because it'll start being called that on Tuesday. It's where x equals 0. It's not always that meaningful a value, or a number. So it may be the case, for example, in our fictitious smoking example, that this is only true for smokers. It may be the case that for non-smokers, this isn't really true. So putting 0 in here doesn't mean everybody just stops, everybody just lives to be 90. Excuse me. So maybe the case that that's actually useless there. What if we had something about, I don't know, predicting something where, let's see, age and predicting. So we're going to have age as the x variable, and we'll predict. Oh, you know what? The height and weight ones are fine. We can go with that. Is there anybody that has a weight of 0? Well, no. So it's actually a meaningless value of the intercept. Sometimes it's actually very meaningful. But it very often isn't. It's almost like it's an artifact to do the calculations. This, again, the way we calculated these is for linear relationships only. You should take a look at that and see that this is a straight line. Back when you were in high school, this would be the n, and this mx plus b would be what that would be. Those are straight lines. Those are not curves. They can't be curves. Right? You could do it for a curve. You could certainly fit. It's called curve fitting. You certainly could fit that, and you get a parabola. You can do it. Right? So you could fit y hat equals b sub 1 x squared sub 1. Yeah, and there's variables like that. There are relationships like that in nature. I mean, it's not ridiculous to think of that. And also, you can think of a logarithmic decline, right? Like a decay function for memory. So it's not a straight line. the logic is exactly the same how you do this. The math behind it's different, but the logic about fitting the curve that has the least squares regression line is exactly the same. One of the things you should look at what's called the residuals. E. They're called E. It's another name for these. Y minus y hat. That's what E is. It's a residual. E for error. Okay? It's prediction error. Now, right now you might think, well, I could put it this way. If you were to draw if you had a scatter plot, you can see that is a straight line. So you don't have, and then you draw. Let's say that's your regression line. What you can look at is a residual plot. And it looks like this. So that's along the x-axis, so the y-axis got E. Along the x-axis, it's got, well, x. And then we should get equals scatter above and below 0. Then you might think, well, I can just do that by looking at that. Yes, you can. And right now, it's more of an academic exercise to think about a residual plot. However, when we start having more than one x variable, more than one predictor, then it becomes a little more necessary to do this kind of thing. So one of the things you can look at is E, the residuals. There should be no relationship between x and prediction error, x and E. None. If you had a residual plot and you had a pattern of look like this, probably means you have a curve, right? Or if you have a pattern where they get bigger as x gets bigger. That shouldn't happen. Why should it be the case that the bigger the x value, the bigger the prediction error? It doesn't make any sense. It shouldn't be that way. It's not linear. But y equals b sub 0 plus b sub 1 x sub 1, or y equals a plus bx, should be, that's a straight line. And that's the curve we fitted. We fitted a straight line. So the data have to conform to that. If they don't, you've got to find another way to analyze your data. So the covariance of x and E should equal 0. They should share no variance whatsoever. Now also, don't go outside the range of the data you collected. So one of the things you do when you're making these, when you're using these kind of models is, for example, with our smoking fake model, we would say, oh, well, that means smoking a year takes a quarter of a year off your life. That was what the model said, right? So you can actually make that kind of, that's the kind of statement you might be able to make. On the other hand, think about the example of how much money I make, right? So you got the floor, that's the intercept, plus the number of years that I've worked here times whatever the increment is, times the PTR. And let's say for me it comes out to be, I don't know, let's say it comes out to be $115,000 a year. Okay, let's just say it comes out something like that. But if I worked here for 1,000 years, I could make $17 million a year. You can't go outside the range like that. It's ridiculous. Or you can say, if I worked here 50 years, I don't think that's possible. Right? You start, conservatively, you start when you're maybe 30, typically. That's 80. You don't work till you're 80. Because you die. Like it'll kill you. I feel like I'm going to die already, and I'm only 49. So, or, you know, it's the example of, let's say you're trying to predict how many cigarettes someone smokes. I give you the cigarette example, and the reason is a friend of mine did some really neat stuff with predicting how many cigarettes people smoke per day. A behavioral example. Instead of having to measure something physiological, he could ask you like 4 questions and predict how many cigarettes you smoke a day, which is a lot less intrusive than taking blood and taking a saliva sample. If you did it using regression, it's a very neat thing. The same guy that did the drugs in hospital thing in graduate school, there's another side project he did, which was a neat little project. you know, you take a look at something like that and you say, well, you can take a look at someone's age. Like, there's a few variables in there, and you say, well, okay, but what about for kids? What about if the age equals 2? Well, 2-year-olds don't smoke. So you can't go outside the range and make that prediction. Right? I know there was that baby on YouTube. But, or as a kid on a TV show once, a kid was like smoking since he was 4. Way to go, kid. That's awesome.
There's someone that smoked since they were 7.
There are people, years ago that used to happen. That used to be a thing now. I mean, that wasn't uncommon.
He's like my age.
That's bizarre.
Yeah.
No, that's and of course, like I said, 50 years ago, if you said when you start smoking, I was 10, people go, yeah, that's about right. I mean, I'm thinking back, my dad told me the first time he smoked when he started smoking, he just smoked one day in his house. He was 14 years old, and I think when Dad was 14, it would have been 1957. Yeah. And, is that right? Yes. So he would have, and I can just exactly picture my father, because he would have had like jeans on and a white t-shirt, and he had all kinds of crap in his hair, and he always had his lip like this, like he was Elvis, because that was what my dad looked like. And I can just see him lighting a cigarette. Totally. Anyway, apparently his mother said, Richard, you smoking? It's going to stunt your growth. And he said, Mom, I'm 6'1" and I'm 14 years old. And she went, and my grandfather said, the boy's got a point. And that was it. From then on, it's like, smoke him up, Ricky boy. It's a different time. But now, you don't hear kids smoking when they're 4 or 7 because it's weird. And you wouldn't put that into a regression model when the youngest person you had was 20 in your prediction equation. Right? It becomes a meaningless value. Or if you're predicting something about likelihood of contracting some, I don't know, a sexually transmitted disease, or we have a new name for them now, don't we? What are they called now?
Infection.
What's wrong? We have perfectly good words. We can change them. And you probably have one of the things in there be number of sex partners. That's going to be one of the things in the regression model. In fact, we probably make a nice model predicting likelihood of getting whatever it's called now equals some constant. That would be the B sub 0 with the A, plus some number times the number of sex partners you have. That's a pretty good guess. It's probably linear too, right? But if you put in 0, you can't get those. You can't get anything like from a toilet seat. It doesn't work that way, right? I took health in grade 7. I know you can't get that. So you can't go outside the range. And it's very tempting, because it's so tempting when you have a model that says this equals this plus this. You go, oh, really? You mean I can just put any set of numbers in there? Ooh. No, you can't. You can put in numbers that are in the range of that go along with the stuff that you collected. And people are way too tempted to do that. And it is tempting. The first time you see something that spits out of a computer and it tells you life expectancy equals 90 minus 0.25 times a year's smoke, you go, holy crap, that's great. Okay? So it's a little easy. A little tempting. It's too easy to do. Don't do it. Questions about correlation and regression? Okay, you have a quiz on Tuesday. And remember that it's on everything from the last quiz up till this quiz, up till I say goodbye. Also, the Psychology Honors Thesis Conference is tomorrow, NW 200 at 1 o'clock. Be there. It'll be awesome, and especially those of you guys that want to do the honors degree next year, do the thesis. It's something I think nice for you to see, and support your fellow students. Thanks, guys.